Good morning, everyone. It's very nice to be given the opportunity to speak here today. It's been a great joy to be at this joint pro-am meeting. I've learnt a huge amount already. But I should say from the outset that I am firmly at the amateur end of the spectrum. Okay? So with that in mind, I thought I would say a little bit about where my observatory is, because it's not in La Palma or Hawaii or the Atacama Desert, unfortunately. Okay, it's no exotic place like that. There it is, right in the middle of the UK, in a place called Sheffield, which I appreciate many of you in this room have probably never heard of. But you go back 50, 60, 70 years, and it was famous for steel production and steel export all over the world. It was called the Steel City. It still is by its locals. But unfortunately, those days have gone. So now I show it in context with respect to our current major world export, Manchester United Football Club. Okay? So everyone's heard of Manchester United. Hands up those people who haven't heard of Manchester United. Okay, the Americans own it, so it's a truly global product. The main point here is that this is a city, Sheffield's a city of 500,000 population, so it has a substantial light dome. I live on the western periphery, so you can't do broadband imaging. I've done some narrowband imaging, but spectroscopy does lend itself a bit more easily to such conditions, and so that's what I'll be talking about today. So here's the outline of the talk. Some background. First of all, why should we study Cepheids? Well, I mean, I don't think I need to give this audience the tutorial on Cepheid pulsation, but I need to include something just for the sake of completeness. Okay? The second point here, why study this target, V1334 Cygni? This is a more substantial point, and at this point I should do the expectation management. Okay? So I am not going to show you some wonderful new discovery about this star. Don't get your hopes up. All right? This is a talk about a technical challenge for amateurs, because two things, at least two things. First of all, the radial velocities that we're looking to represent accurately here have a maximum magnitude of about 4.5 kilometers per second. So for amateurs, that's smallish. Okay? And I'm pushing my rig and my processing stream as hard as possible to try and get the last sort of decimal place, if you like, from my data. The other thing here is that the radial velocities are comprised of two components, a pulsation component and an orbital component. And we'll see about the way in which I try to dissect out those two components. So I'm trying to wring the last drops of goodness out of my data, if you like, at this end of with this star. So I'll talk a little bit about the acquisition methods, my rig, and how I acquired the data, and how I extracted features and Doppler shifts. But then we come to the meat, if you like, of the talk, where I'm going to draw on a recent paper by Gallene et al. This was published a year before I got the first set of data for this study. And they have done a nice model of this system where they show how you can dissect the radial velocities into an orbital component and a pulsation component. And at this point, I want to concentrate on the fitting of a sinusoidal curve to my pulsation data. And I want to convince you that it is truly sinusoidal and not just some quirk of random chance. Okay, I'll take some time trying to do that. And look at the accuracy of the period determination, which I was surprised at how accurately it turned out. And maybe I shouldn't be surprised. I don't know. You tell me later. But anyway. And by chance, there is some photometry data for this star during the period I was observing. It turns out to be the one courageous observer on the AAVSO database doing visual observations, but hundreds of them. And I tried to make a link at the end between the photometry and the spectroscopy. And then the sun. Okay, so let's. You don't see it. Okay, this is well-known stuff. Here's the typical light curve of delta Cepheid, the archetypal Cepheid variable. They show regular oscillations between 1.5 days and a few weeks. Okay, and I guess the story goes like this: that there's a lawful relationship between the luminosity of the star, or its absolute magnitude, and the period, shown on the right-hand panel there. So I guess the story is that if we have a new star with new Cepheid which pulsates here over sort of 8 days or something, we can read off its absolute magnitude, and from its perceived magnitude, its observed magnitude, we can compute the distance to the star. So if we know which system the star's in, we can estimate the distance to that system. That is my understanding of the Cepheid variable story. Okay. But this is what I want to focus on, is the technical challenges that I faced anyway, in trying to understand my data. So the radial velocities of the pulsation lie between plus or minus 5 kilometers per second at the very maximum. So that's the very maximum. I'm looking at trying to resolve 0.1 of an angstrom with my rig. But there's the other complication that the raw radial velocities I get are compounded with an orbital component because it's a multiple star system. So I've got to try and dissect out that orbital component. And then I'm going to look at determination of the period. How accurate was my determination of the period, and what does the search space look like? I think that's interesting. Okay, so data acquisition. Here's my rig. You've already seen a picture a bit like this. Jack Martin showed something similar at his observatory. Mine's a slightly smaller scope. It's a C11 compared to Jack's C14. I've now got it on a metal pier. I'm very proud to own a metal pier bolted to the floor. Hey, how cool is that? For the first part of this study, I had a home-built wooden pier where they had a bit of flexure in. So I convinced the wife and the neighbours that I could bolt my metal pier to the ground. There's a Mizu 200 mount, which is a nice mount. It hasn't got any gears in. It's friction drive, no backlash. Slashed on C11. I've got a cheap refractor sitting on top there with a ZWO camera that I use to find stars and occasionally do photometry. I haven't got any photometry data here with this study, but I sometimes do concurrent photometry with the spectroscopy. And there's the infamous LIRES spectroscope hanging off the back there. And I'm using the 2400 line per millimetre grating. The other thing, which was, this shot was deliberately taken from this angle to highlight the other feature here. My observatory also contains plenty of trees, houses and lights. Okay? So, and spill coin. As a hazard I don't have to put. The point being that I wanted to gather more data for this presentation in the later part of the spring, but I couldn't, because even though the star set sometime around midnight, it's set below my house 3 hours earlier. And so I just lost the ability to see it. But my horizon is very poor. I've got a small part of the sky that I can see at any one time. But I okay, so you acquire the data, and then I reduce it in the usual way to produce one-dimensional spectra. I did that in ISIS, which is very popular in the amateur community. I think Jack mentioned that the other day. I've recently started using Shelyak's in-house system called Demetra, which was originally designed for a low-profile spectrography LP. But I've managed to supercharge it, if you like, with some extra Python code to do high-resolution calibration as well. So if anyone's interested and want to talk about using Demetra for low-res work, I'm happy to talk about that another time. Beyond the simple data reduction, I then got to work hard to extract my radial velocities, and I would be lost if it wasn't for the scientific Python initiative, and in particular AstroPy. Speaking to one or two people here, I understand that the professionals also use AstroPy sometimes. Good, yeah, I'm not alone in it. It wouldn't leave home without it. And in particular, there's a sort of offshoot from AstroPy called Specutils, which does exactly what you'd expect it to do. It's a spectroscopic utilities program. And again, this does all the things that you don't want to waste time coding up, dealing with FITS files and chopping spectra up and fitting Gaussians and things. It does all that stuff for you. The final thing that I'd like to draw to your attention, perhaps less well known, is that I wrote all this code in a Jupyter notebook. Hands up those people who ever use Jupyter notebooks. Oh, quite a few people, good. Again, I thoroughly recommend it as a way of writing code. I could spend a whole talk on why it is a good idea, but a Jupyter fundamentalist would say that you should write the paper and incidentally include the code. Okay? It encourages you to write documentation in a proper way around your code, and also chops your code up into little segments that you execute independently. So that was how I did this. So down to some data. Here's some typical data. One spectrum. It shows a region around the H-alpha line. It's a fairly narrow absorption line. There's the nominal sort of earthbound reference. This is a slightly red-shifted line then. And I'm also showing here one of the telluric H2O lines at 6543.9, which I'll talk about later. So that's a typical spectrum. So what I did, I tried to extract the position of this H-alpha line, and I proceeded as follows. I first of all tried to take out any notional continuum, which I assume linear, by fitting linear segments here and here. Again, Specutils does all this for you. It has functions for doing this. You just incorporate them into your code. So you remove any linear slope here, and then you can fit a Gaussian, and you can define in Specutils the limits over which the model is fitted. So this Gaussian is fitted with respect to this narrow part of the absorption line between those two dashed lines there. And you have to choose, somewhat automatically in the end, but you choose that region for each spectrum, because of course this is moving around, this is shifting backwards and forwards. Zooming in a little bit to give you some idea of, so we're now looking at plus or minus a couple of angstroms here. You can see how the Gaussian curve fits into that sharp line and picks off. I pick off the minimum there as my absorption line. So extracting Doppler shifts, I guess you all know about this, but let's just work through it. And in particular, here, I finessed the calibration by using those water absorption lines, because there's plenty of them around the H-alpha. So I chose the one that was reasonably well defined and nearest to H-alpha, and I shifted all the spectra so that they all aligned with that reference. The shifts were very small, but I'm trying to wring the last little bit of accuracy here. So I shifted everything with respect to that water line. Then, of course, find the actual shift in wavelength with respect to the nominal hydrogen alpha line. and find the Doppler shift in the normal way, the non-relativistic version of the Doppler shift. And finally, I make a heliocentric correction to find the true radial velocity v sub r. So when you do that, this is what you end up with. So this is a plot of the radial velocities I extracted in the method I just showed against time. And you'll see that I've got a break in the time axis about here because there was a few data points gathered in late summer 2019 and more gathered in December 21, January 22. I thought, I can't come to the meeting with 5 data points, so I ought to try a bit harder. So that's why that break is there. It's actually a much longer time stamp over a 3-year period. So that's great, but how can we interpret these data? Okay, the scatter, look at the scatter, it's fairly clumped around those 2 values there, plus or minus 10, and it doesn't indicate a sinusoidal curve in any sort of way. And we know from the published work that the amplitude of the pulsation velocity should be around 4.5 kilometers per second. This is nowhere near that. Okay? So what's going on? So this is where I went to that publication and tried to use what they had provided to make sense of my data. So the thing is that V1334 Sydney is a multiple system. It's a triple system actually. The Cepheid itself has a very close but faint companion, and this pair is orbited, or is in orbit with, a much wider, more widely separated companion. So Gallene et al. Provided a model of the radial velocity of the Cepheid split into components due to the wide pair orbital motion and the pulsation. Okay? So this is what I made use of. And in case you're concerned about the third component, I was reassured, and Gallene were reassured, that the spectrum, the visible spectrum, is dominated by the Cepheid itself. So that faint, tightly coupled companion is not hugely significant here. So how do we extract the orbital component? Well, we should solve the orbit, shouldn't we? Well, here's the thing. I guess orbital mechanics have been known, well, since Newton, and since someone first bothered to have to solve this problem. It's not completely trivial. I mean, I'm an amateur coming to this for the first time. This is probably, you know, orbital mechanics 101, but, you know, I have not done orbital mechanics 101, so I did it on my own. It's a tricky problem because it's 3-dimensional geometry and classical mechanics. You've got this elliptical orbit in space, which is projected onto a plane in front of you, of course. And my first attempt to try and pinpoint my data on the orbital trajectory was that I digitized the figure in Gallene's paper and used data thief to reconstruct it. And suppose people who've used data thief to rip off someone's data and use it. Oh, come on. No, obviously give you attribute where you got it from, but it's very handy if you don't have access to the raw data behind their graph. Digitize it, you can reconstruct the graph in a fairly accurate form and use it as is. Obviously you attribute it to the orbits. But I got fed up with that and I thought, hold on, I think I can do this, yeah? It's 3 equations and some parameters. The equations are in black, the parameters are in the orange boxes. It's not completely trivial to solve because it's not analytic. There's a bit of root finding here in that equation, iterative root finding. And as someone coming to this for the first time, I found it curious that it was quite difficult to find a principal derivation of these equations. Everyone uses them, but no one derives them. So I kind of eventually determined that this was the right form of the equations and solved them. And of course on modern computers, you've taken your finger off carriage return and it's solved it. It's not a big deal, but I suppose you go back 30, 40 years and it would have taken a significant time. Anyway, you solve it and you get the blue trace here. That's the orbital solution. And here are my data, the red dots. I should emphasize that there's no fitting going on here. All I'm doing is I'm picking off the points on this orbital diagram where my data were. So because they were collected in 2 tranches in 2019 and then late last year, early this year, they occupy these 2 spaces in the diagram. So if you do that, you start to get something a bit closer to what you might expect as radial pulsation velocity. So I show, for comparison, the original untreated radial velocities, these are the red points I showed earlier. Now, when you subtract off the orbital components, they all start to lie a bit closer to this line here, which is what you'd expect. Okay, and it's closer to this observed amplitude of 4.5 kilometers per second. So that's good. We're getting closer. We're gradually getting there. So what happens next? Well, we try and fit a sinusoid. So I've determined phases for my data in the normal way, and try to fit a sinusoid of this form. And I'm looking for solutions where this mean is 0, because, you know, in principle, the pulsation should have a 0 mean velocity. And that requires that I adopt an appropriate system velocity. Yeah, I should say, I should emphasize that this curve here, the observant in the audience will notice it doesn't have a mean of 0, because this includes the overall system velocity as well. So by fiddling with the system velocity, you can ensure that this is 0. And also conventionally, the initial phase is 0, so I'm going to choose an initial time point t0 appropriately. So here's the orbitally extracted, sorry, the radial velocities with orbital components subtracted, where I fitted a sinusoidal curve. And I'm varying the period, the amplitude, the mean, and the phase offset, but then I'm choosing the system velocity to ensure 0 mean, there is 0 mean here, and the initial time in the ephemeris so that the curve starts at 0, 0 here, okay? So at this point, I could say, blur your eyes and believe me, it's a sinusoidal data, yeah? But I'm going to do some work to try and convince you a bit harder that it really is. Just blur your eyes for a moment. So, sorry, before I move on, I should draw attention to the, up here, I've drawn the equivalent delta lambda, the wavelength shifts here, which I've given rise to these Doppler shifts. So, I mean, for me, that's small. It may not be small to you guys, but that for me, with my read, that's quite small. So, let's compare with look on the right, there's Gallene et al.'s beautiful sine curve where the data points fit perfectly on their curve. Isn't it beautiful? And there's my old thing, look at that. But look, it's not fair, yeah? They've got this, and this, and I've just got this. Right? That's not fair, is it? Okay, so, I mean, look, it's a 2-metre instrument. They've got a big bench-mounted spectrograph. I've got this. This is flapping about in the wind. It's made out of sheet metal. Okay. This is bolted to the floor. This looks a bit more substantial. I'm making excuses, but you see, you know, they're going to get much better. Anyway, that's the way it is. So in more detail then, the RMS error for, and I'm going to use this metric of merit, if you will, quite a lot. The RMS error for the best fit here was 1.55 kilometers per second. I don't know what theirs was, but it's going to be tiny, isn't it? But interestingly, the amplitude that I get, 4.85 kilometers per second, isn't far from their amplitude. It differs by 15%. Even more curious is that the period I get is very, very close to the period they get. It differs by 68 seconds over 3 1/3 days. The system velocity that I had to impose to ensure a zero mean here is 0.85 kilometers per second. Their system velocity was minus 2.65, which incidentally isn't the velocity given in Simbad. If you look this up in Simbad, the radial velocity is minus 1.8, I think, which comes from an earlier study. So it's a movable feast. It will move around depending on how Simbad keeps up to date with its most relevant information. I'm sure they won't include my data, but you can see it does vary a little bit. So now I want to try and convince you that my sinusoidal fit is sinusoidal, right? So the first thing I'm going to do is a visualization exercise. Just unfold the diagram across several epochs with phase going up to 3, and I have to look here to see. It looks a little bit more periodic and sinusoidal. You don't have to blur your eyes quite as much. Okay? But let's do some testing. So let's bring out the big guns. Kolmogorov-Smirnov test for fitting, for deciding whether the data are drawn from a specific distribution. I use this even though I would probably have told people I taught in a previous incarnation that they shouldn't use this, because I always say, look, if you don't have an intuitive understanding of a statistical test, don't use it. Don't just press the buttons. Right? I don't have an intuitive understanding of the Kolmogorov-Smirnov test. I didn't have the time or patience to set up a load of synthetic data sets whose ground truth I knew and then run the test. That's the best way to understand these things. Just generate lots of spoof data to plot that whose ground truth, you know I drew it from a Gaussian, I know I drew it from a Poisson, whatever, and then try and understand the test. I didn't do that, I just turned the handle, right? And you get an answer that is encouraging, which is encouraging. So do those data come from the arc-sine distribution? Yes, they do, because if you turn the handle, the significance level of P is 0.05. I think I could have pushed it a bit harder than that. There's this so-called Kolmogorov-Smirnov critical value of 1.36 over root n, where n is the number of data points. Here that works out to be 0.36. KS statistic for this exercise is 0.19, and then you recite in a sort of monotonotic drone, since KS is less than theta, we do not reject the null hypothesis that data comes from the sinusoidal distribution. Okay. So I've turned the handle. I've done it. Technically, it looks like it could be sinusoidal. They've drawn from a sinusoidal distribution. But there's more to this than just is it drawn from a sinusoidal distribution. It's what about the ordering of the data? And this is an exercise which I did because I think I can intuit a bit more about what's going on here as well. So you could take data drawn from a sinusoidal distribution and they could just be randomly assigned phases, and you wouldn't end up with what looks like a sinusoid. So what I did is I took my data, didn't change the values, but I shuffled the phases around randomly. Okay? And if you do that, here's an instance, 1,000 times, you end up with a histogram here of the RMS error for the best fit. So down here is the actual fit, so the actual phases you get from the data. And here's the histogram for my synthetic shuffled exercise. So I was encouraged by this to think that, yes, I didn't just, if my data had fallen somewhere over here, I might start to think, it's not really sinusoidal, I just got slightly lucky. But it isn't. You can generate randomly some things that look almost sinusoidal. Of course you can. But most of them are not very good fits, much higher RMS error. So let's take stock then of where we are and look at what we are getting here, given the instrument's limitations. So the best fit error was 1.55 kilometers per second. That corresponds to 0.034 angstroms. And let's compare that with some measures of resolving power of the rig. So the dispersion here is approximately 0.12 angstroms per pixel, so that's 5.5 kilometers per second per pixel. The resolution I've got is about 13,000, and I reckon that makes the smallest resolvable wavelength difference to be about 23 kilometers per second, equivalent 23 kilometers per second. But we're not resolving differences in the line. I'm not trying to do this here against the bright background. I'm not trying to do resolve. Are there two peaks or are there one peak? I'm just doing this. Is that moving? Yeah, different exercise. So we shouldn't be too surprised that we can get better than the sort of nominal resolving difference there. But it's encouraging that we are pushing the instrument close to its possible limit, I think, anyway. This was interesting for me. You can see I'm a bit of a dog with a bone, as we say in England, with the data. I like to really drill down and see what's going on. It's just the way I am. So here is a plot of the RMS error against the period as you vary it from the nominally best fit. So when you use the period of best fit, it's 68 seconds smaller than Galene's. By definition, you get the minimum of this curve here, the smallest RMS error, around 1.55. Yeah? As you vary the period away from that best fit value, you get a sort of quadratic variation in the RMS error, like this. Again, that's pretty much what you'd expect. Hurrah! Everything's behaving nicely, isn't it? But then when you zoom out, you get some slightly weird effects. There are these beat sort of things going on, or resonances. So there's the little bit of the quadratic I showed on the previous slide, but now with this much bigger time scale, you see you get these other little resonance peaks and dips. And now let's look at the really big picture. Oh, modern computers, they're so fast, this doesn't take any time at all to record. You get some really, it's patterned, it's not completely chaotic. Here's the segment I just showed earlier. There's another sort of close-ish fit here. And in the interests of full disclosure, the very, very best fit is actually given over here with a period of about 1.4 seconds, yeah? But it's not a robust area of the search space. So, so the true global minimum for me actually is around here. But this is a much less robust solution. Now, I conjecture, I suppose I could have tested this, I conjecture that with more data, these two regions of solution would survive, this would just fall away. That's my belief at this moment in time.
No, to resolve this immediately, it will stay because that's an alias frequency.
Yeah.
So if you looked at this in frequency space,
Yeah.
you would get a best fitting frequency of 0.3 cycles per day, and then because you have sampled your data basically once each day, periodic gaps in the data set, you'll get a period of 1 minus 0.3 cycles per day that equally fits the data, and that's 1.4 days.
Okay.
So that's just an effect of the sampling of the data, basically.
Okay. So it won't disappear, but it'll it's what you just said.
You need data from a second site, then it goes away.
Okay. All right. Thank you.
Break the observing pattern.
Okay, that's right. Okay, finally then, I got lucky. There's some photometry data out there. How do we go about doing the comparison? Well, here's a cartoon of the radial velocity in the Earth frame. Here is the graph from the star's point of view. It's just flipped over. And if we think for a moment, then we have that when the velocity is 0, we will be at the extrema of the radius. So the radius looks like this. It's not supposed to be 0 there. It's a cartoon just showing how it varies. Yeah? And then I did try and drill down and find out what the consensus is here, and perhaps I should have tried harder, but the best I could find on interpreting this was some lecture notes on variable stars. Okay, I mean I'm sure it must be out there in the more sophisticated literature, but this guy said in his lecture notes, and I believe him, that maximum luminosity happens with the radius at intermediate values, but increasing at the maximum rate, which is here. So maximum luminance appears with the radius at intermediate values, but increasing at the maximum rate. And then he would have us believe that minimum luminosity happens with a radius at approximately the same same as at maximum, but now decreasing at the maximum rate. So that's why I've drawn this luminance curve like this, which of course when you turn into magnitude is going to get turned upside down. So after all that messing around, it looks like the magnitude is going to be in phase with the radial velocity. That's my conclusion anyway, after studying his lecture notes. So here then are the photometry data. It's from one observer, all visual, and you have to blur your eyes quite a lot here to believe that this is sinusoidally varying. Go on, blur, blur. So what I did, I helped the blurring by binning it into, I don't know, just binning it a bit more. So if you do that, you can see there is a pattern here. It's a little bit more obvious. And you can fit a sinusoid to this, and it is almost in phase with the radial velocities from the spectroscopy. Interestingly, the best fit period is also pretty bang on with the one I found. So I was again encouraged to see there's a link with the photometry here, which was very kindly supplied by this courageous observer who observed this star over a two-year period. So, in conclusion then, I've used high-resolution parameters, high-resolution spectra around H-alpha to extract pulsation radial velocities for a Cepheid variable with a period amplitude of about 5 kilometers per second. And this required access to an orbital solution to disentangle it from the orbital component. And I believe they really show sinusoidal variation. I laboured quite hard to convince you that it was not just a quirk or a fluke or something. Yeah? And the fitted period is within some small percentage of the published value. And there's some low frequency resonance, which I defer to the learned gentleman for sinusoidal fitting with his interpretation. And there's a nice relationship between the the curves I found with the spectroscopy and the theoretical correspondence with those for photometry. If I was to do this again, I might do, who knows, I don't know. If I was to do this again, then I would probably use my medium resolution grating. I just happened to have my high resolution rig set up, and I was working around H alpha for other things, so I didn't disassemble it every night for this particular study. I would use a medium resolution grating, try and capture a part of the spectrum with more lines, and use more conventional methods of cross-correlation. I suspect that I should be able to increase the accuracy of the period determination and so on beyond even what I've shown here. But given the methods I've got here of just using the hydrogen alpha lines and so on, this is about as good as it gets. Okay, that's it. Thanks so much. Easy questions only.
Did you say that it was a multiple star system?
Yes.
And you took into account only a kind of the closest component which produces the changes in the radial velocity on its orbit. So are other components taken into account, or maybe they don't even influence the
well, it's supposed to be a triple system, as I say, so there's a close binary pair where there was a reference there, I can't remember now. They say that the close binary companion is not really influential in the visible spectrum. I think they may have had to see it in UV or something, I can't remember. But it doesn't influence the visible spectrum much. So I am looking at the Cepheid. But then there's this wide companion in orbit where you do have to take into account the orbital contribution.
And I think I have a topic for the next conference. Because for the last 7 years I was involved in monitoring Polaris. And I think we have the largest database now with over 300 spectrum. I just didn't think about talking about it, but yeah. Come back in 2 years.